Hello there, math fans. Dr. Andy Lovelace. I've been making a lot of examples of 2D curves and talking about their curvature for my course. This is a whole bunch of examples. I got a little overzealous. This is not really for my students. It's just for those that say, I need more examples. Can you give me more? Well, how about 16 more? I overdid it a little bit. But I've been enjoying making these osculating circles. So these are the formulas. This is the 3D formula for curvature. Check out my previous video on that. Here's the 2D formula, and then I've tried it out on a whole bunch of 2D curves. Here we have a circle, then we have an ellipse, then we have a parabola, and watch my future videos where I actually do calculations. This is just going to be more of a showcase. The circles you're seeing are what are called the osculating circles, and I mentioned in my previous video how I think about curvature, that I think in terms of the radius it forms, which is 1 over the curvature. Okay, so anyways, for a circle, you don't see an osculating circle because the radius of curvature is 2 always for this circle of radius 2. So more interesting would be something like an ellipse. So here's an ellipse, and here's a bunch of circles so you can sort of see what the radius is like. And I can sort of let that go. And you can see that the radius, the turning radius is smallest, which means the curvature is the most at those corners and at the places where sort of more, it's more eccentric, it's more spread out. That's it. That's where you're turning the most if you were going around the outer edge. So for an ellipse, the maximum curvature is on that edge. Now finding the formula for the curvature, that's going to be a big mess, but it's an interesting idea. For a parabola, you know, the biggest curvature is going to be right there at the vertex. That kind of makes sense. That's when you're turning the most. This is different than slope. Okay, let's keep going. Here's a cubic. I solved this in my last one. It was some work to prove, but actually there's 2 places when the curvature is greatest, and it's like somewhere over here and somewhere over here. And those are when you, if you were looking down from above, it's when you would be turning the fastest. So let's kind of circle the places where you have greatest curvature. Okay, at that point, I just started to think of what other functions could I think of. So maybe you recognize that. It's actually a hyperbola. It's y equals 1 over x. That's what this is. This is 1 over x. This is y equals x to the third. It has some interesting spots there. This is y equals x squared. This is a hyperbola. Sorry, this is an ellipse. This is this one. So it turns out to be right here on this y equals x point. There you go. There'd be something similar on the other side. That's when you'd be turning the tightest if you were driving on that road. You might guess for the next one. This is the one the students do in the homework, is the log function. The log function, the curvature, even though it has an asymptote here, the curvature down here on the log function is close to 0. So curvature is not the same thing as slope. So the question is, where does the log function bend the most? It's a question most students have never encountered. But it's somewhere in there. Can you find it? What is that value? And what's the curvature there? And what's the radius of curvature? Interesting question. E to the x, I asked this on an old exam once. It's actually pretty nice. Where would that be? This is y equals e to the x. It should be a very similar answer to this one. The derivatives are really nice because this is e to the x and this is e to the x. There's a little bit of algebra in taking the derivative and setting it equal to 0, which you might see if you can find it. What about this one? This is like the bell curve, so I basically took like a bell curve. The radius of curvature is biggest at 0, but interesting, there's 2 other spots where the curvature is pretty big. In fact, here's what the curvature function looks like if you lay it on top. So curvature is big at 0, and it's also big at these couple other spots there and there. And incidentally, I didn't do that for some of these other functions, but for e to the x, the curvature function looks like this. It's biggest kind of right there. For this function, the curvature function looks like this. It's biggest at those 2 spots. So it's just another fact about my curve. The curvature is biggest at those 2 spots that maybe people haven't thought about before. Okay, so let's keep going. This is the sine function. Where is the curvature greatest? for the sine function. If you're walking along the sine function, in fact, if you're right here, your slope, it's almost like you're a straight line. You're approaching, so the greatest curvature is going to be at these high points and low points. Let's see that in action. I'll move this over. Again, when the circle is smallest, that's when you're making the tightest turn. I find the osculating circle is definitely the way I think about this. Let's keep going. So that was sine. So we did, this is actually like y equals e to the negative x squared. Something kind of like the bell curve. This was sine. Again, I was just trying to think of more functions. Here's arctangent. When is it bendiest? Well, it's going to be somewhere in here and in here. Where is that? I have no idea. I didn't solve the question. But it's this picture. It's actually not that. The curvature is going to be pretty small. But there's these two spots. So there's a challenge question for you. Might need a solver for it. I didn't solve it. So there's an unsolved problem. A problem that can be solved. A problem that I have not solved. Okay, so here is what's called the cardioid. It's a heart-shaped thing. And if we run around it with studying its curvature, it's kind of interesting. But the curvature is interesting right when you get close to here, because it actually gets really big in a very small amount of time. So the radius curvature is really small. Something weird is happening there. So something sort of weird is happening there for the cardioid. And then lastly, I thought we'd do I think you could say a lemniscate. I don't know if I'm saying that right. I've never heard anybody actually pronounce it. I should ask around. But it's the infinity symbol. So where does the infinity symbol have the steepest, not the steepest, have the greatest curvature? And it's on the edges. It's slow. Here it comes back around. Boom. So the greatest curvature is here and here. So that was a lot of examples of 2D curvature. I hope that gives you a sense of this curvature function, the fact that it's just giving us something else to measure. I have one more thing to say about curvature, but I'm going to leave that for another video. All right.